stochasticity might come in and why stochasticity might come in. So I'm just going to revisit some of these things from a fairly high-level perspective. Before I go into that, this morning we also had a bit of a genealogy of the physical predecessors of the climate models, the people that developed the physics that go into the climate models, and I'll suggest that perhaps one was left out now that we're moving into a more stochastic perspective, right? I mean, the introduction of an explicitly probabilistic way of thinking about physics is a relatively recent phenomenon in the physics community, and of course Ludwig Boltzmann plays a really important role in that. So we've talked about the need for subgrid scale parameterizations in these models because we have, to represent the atmosphere and the ocean by grids with finite resolution, and as a result there are small scale processes that are not going to be represented in the model, and which processes are represented and which are not depend on what your resolution is. But there are, as we've heard, many orders of magnitude of physical scales that are relevant to weather and climate processes, and any real model will have some represented variables, or some represented scales, and some unrepresented ones. Now, why this is a particularly difficult problem is that we have nonlinearities in our equations of motion, and we have a finite resolution, and the coupling of those two implies that there is an upscale influence of the unresolved processes on the resolved scales. If that didn't exist, we wouldn't need to represent the unresolved scales. But because the unresolved scales are influencing the resolved dynamics, we have to worry about that. And just a simple example would be, to make this more concrete, we can talk about an averaging operator, which describes our resolved variable. This you can think of as being an average over the grid box, so a spatial average, but there's also an implied temporal average often in these. And then we have our eddies, or our deviations from the grid box average. And if we look at something like an advective tendency, so the rate at which fluid flow is carrying along some quantity in the atmosphere or the ocean, this average can be decomposed as the product of the grid box averages plus an average of the product of the deviations at the subgrid scale, averaged again over the grid box. And because, again, these can have an influence on the dynamics, we have to represent these somehow. And so we end up with what's sometimes called a closure problem or parameterization problem. We want to represent the unknown subgrid scale influence on the, the influence of the unknown subgrid scale quantities on the resolved scales as some sort of function, or we would need to represent them in terms of the variables that we do resolve. Now, if we have a very large separation of scales, we've heard this comment made before, then we can argue that, now, getting this function is another challenge, but in principle, we would expect, if in the presence of a large scale separation, that the upscale effect of the unresolved scales could be represented as a deterministic function of the resolved variables. So an example would be something like some of the cloud microphysical parameters that we talked about, where there is a very large scale separation between the individual cloud droplets and the scale of our grid box. In contrast, if there's a limited scale separation or no scale separation, then it's arguably more appropriate to represent the upscale influence of the unresolved scales as a distribution conditioned on the resolved variables, because for a given realization of the resolved scales, there may not be a unique upscale influence in the absence of this large scale separation. And this is a general framework for the notion of the stochastic, explicitly stochastic subgrid scale parameterization. Now, just note that even these deterministic parameterizations may have probabilistic thinking underlying them. We saw an example of that in Andrew's talk this morning, again talking about the cloud microphysical parameters, where we can think about distributions of these quantities and average over them. So we're not actually going to be sampling necessarily because of this large scale separation. It would still be a deterministic representation. So there's room for probabilistic thinking, even if it's not explicitly stochastic. As a way of illustrating the extent to which we might expect scale separations to obtain in the real world, and this is an example from the ocean, but Chris showed a very nice example from the atmosphere as well. This is a visualization by NASA of surface ocean currents based on a combination of remotely sensed and in situ observations. And you see all of these various eddies around the ocean, these swirling, I don't know which ones are cyclonic and which are anticyclonic. It's hard to tell from this visualization, but they're swirling around. And I think you'd be very hard-pressed to argue that there's a clear scale separation here. And it's also really important to realize that when it comes to determining what the resolution of a weather or climate model is, often that decision is made by computational constraints, not by where there might happen to be a spectral gap, should that even really exist. Okay? So it is very often the case that there is not a large-scale separation between the things that are resolved and the things that are unresolved. So this issue of stochastic parameterizations has been discussed for a couple decades now anyways, and there's actually quite a nice recent review article in Bulletin of the American Meteorological Society which touches upon a number of recent developments in this area. So if you're interested in this particular question, I recommend highly having a look at this discussion here. So a number of issues have come up in this morning's discussion. So we've talked about, again, the relationship between resolution and the various scales of physical processes. Different reasons why we might want to introduce stochasticity. So one of the issues, of course, has to do with model biases. If there are certain scales of variability that are not being represented and there's variance on those scales that you're not capturing, treating those deterministically in the absence of scale separation can lead to model biases. But as well, in a numerical weather prediction context where we're interested in having an ensemble of different simulations moving away from some initial fairly close set of states, it's a classic problem in numerical weather prediction that the predictive ensembles tend to be under-dispersive. They don't spread out as much as the actual trajectory of the atmosphere moves away from that initial condition. So it's been argued that these stochastic parameterizations can help with ensemble spread. Now, of course, one approach would be just to keep pushing more and more resolution, and at some point you could argue that at least the hydrodynamic contributions to the concerns about subgrid scale parameterizations will be largely addressed. I think it's arguably very far off in the future, but as well there are different reasons people use GCMs, and there are different time horizons on which people want to make simulations. So if you're interested in an ice sheet dynamics and you want input from a general circulation model, well, you want 40, 50,000 years of simulation, and you aren't necessarily going to get that practically from a global hydrostatic model with a 100-meter resolution. So even as we improve our computational tools, there's an argument to be made that there will always be need for perhaps relatively coarse models that can be used for different questions with longer time horizons, or if you want to make very large ensembles or do detailed parameter sensitivity experiments, this issue of having to resolve small scale motions is not going to go away arguably for any time in the near future. We had some discussion earlier on about the difference between sampling from distributions and adding noise. I'm going to suggest that those aren't necessarily distinct, that in, for example, stochastic backscatter type parameterizations, which are often described as adding noise, in a way what we're saying is that there's a tendency in our model which is distributional rather than deterministic, and we're sampling from it, just like you can sample from the individual columns in your subgrid scale model of radiative transfer. So some of these distinctions are perhaps not as clear as might have been suggested. And right, so a few open questions have come to mind that the stochastic parameterization working group might think a bit about, and we've seen indications of most of these as we've gone along. One of the first would simply be, under what circumstances do we need to represent something stochastically? Not all subgrid scale parameterizations are going to require an explicitly stochastic treatment. So are there ways that we can approach this question perhaps in a more systematic fashion? Now, how do we formulate them? Right, this is the broader parameterization question, but within that, we can talk about the use of observations to develop stochastic parameterizations. So these are going to be somewhat more empirical. We can use high resolution models, as we've just heard about, as a way of informing these parameterizations. There are other approaches. So for example, we can use systematic approaches, such as stochastic reduction of more complex models. That is one possibility. And how can we adapt tools from other subjects? So for example, data assimilation or machine learning. And kind of related back to the first is, what are the good candidates for stochastic subgrid scale parameterization? So this is perhaps a more operational question, not just what are the processes that need to be parameterized in this way, but what are the ones that we can probably get a handle on over the course of the next year and maybe make some meaningful progress. So that's a practical subset of the very first question. And I will suggest that even though ultimately we want to use these things in comprehensive weather and climate models, I do think that quite a bit of insight can be obtained by considering some of these questions in the context of simplified systems, either reduced order dynamical systems, or even just single column models from atmosphere or ocean models, where a certain amount of the computational overhead is reduced by considering just, say, vertical processes. So these are some of the questions that had come to mind when I was thinking about how this working group might go. But of course, I invite contributions and questions from anyone who's interested in this issue. Thank you.
Are there any comments, questions for Adam, or thoughts about where this working group may go?
So when you introduce stochastic elements of, these highly multi-dimensional distributions, just from my perspective, it'd be worthwhile to think about their space and time structure, right? So if you introduce a stochastic element in this grid cell, you have to worry about its covariation with the next time step or with the next spatial grid. And I don't know to what extent people have thought about that.
People worry a lot about that. Yeah, it's obviously of great importance. Some parameterizations don't talk to each other, grid box to grid box. Some do to a certain extent. And these are sort of fundamental modeling challenges. So sometimes you may not even want to introduce the stochasticity at the level of the individual grid box. You might want to spatially smooth it so that you induce some sort of spatial dependence. Temporal dependence, I mean, clearly, if you have a 15-minute time step in your GCM, you don't necessarily expect the subgrid scale tendencies to be independent from one 15-minute step to the next. And so trying to have the appropriate temporal structure in there as well is one of these fundamental questions in terms of how these are formulated.
Anything else? Anyone else want to add anything?
In your last point there, it says low order models or single column models, and I'm not sure where intermediate complexity models fits into that, and if like the parameterization of sea surface temperatures as an emulator for the boundary condition for atmospheric models has been proposed, and I think some people are working on that. Is that something like what we're thinking here, or is it? Because you have subgrid scale model in your last green bullet point there as well. That's why I was.
Right. No, I think the use of all models is appropriate in addressing these questions. I guess I was being a little bit parochial. I have more experience with single column models than I do with using intermediate complexity models in this context.
Anything else? Any other?
I guess for me, the key to helping with the time and space scale is a physics model that is somehow governing your basis functions for. They have to somehow satisfy some physical laws themselves. So. So that usually means you have your equations of motion and you have to it's like you reduce that system, or they have modes of variability, like, but those modes have to be time space type of modes that also satisfy the overall conservation laws that you think they should. So I think that's really the way forward in terms of either having functional, maybe some applied math approach to this, rather than just a stochastic and functional form approach to this. So that I think that is an important gateway.
Obviously, respecting the physical laws is critical, as in any parameterization. But I don't see these as being, in essence, different from a deterministic parameterization. And most deterministic parameterizations do not follow directly from physical principles, although they will satisfy physical constraints. So if you have a some sort of representation of mixing that's taking momentum from one place to another, as long as that momentum is conserved, then that particular component or that particular conservation principle is respected. And I don't see that, having parameterizations which have an element of indeterminacy in them are necessarily any more inconsistent with physical conservation principles, except to the extent that, you don't want them to start injecting a whole bunch of energy or something which isn't really there. So you have to think about these.
Yeah, but I'm saying something different, which
Okay.
is that the time and space correlations
Yes.
are very. There's a lot of degrees of freedom in this possible system, and so I'm saying that the laws that govern these conservation can help you figure out
Sure.
what is the appropriate
Okay.
time and space scales.
Right.
So kind of in that same way, when I think of separation of scales, I immediately think of homogenization.
Yeah.
And there's just so many tools that can take these types of systems in a physically reasonable way,
Yeah.
right, and map one complicated system into something similar. So I'm not sure exactly what kinds of homogenization problems would show up in cloud physics, right? But I can certainly think of things in like waves and sea ice. So I just wanted to bring that phrase up because there's a whole field of applied mathematics that is really designed for that specific problem. So
No, that's clear. And it's a question of terminology. I was thinking of stochastic reduction and homogenization as being similar.
exactly, yeah. I mean, it sounds the same to me. Just
And of course, one of the challenges there is that, again, we are dealing with systems without a strong scale separation. So how do we accommodate the fact that many of these more formal approaches tend to be asymptotic, right? When in theory, these reduction or homogenization results are valid as epsilon goes to 0, when epsilon is 0.8. And this is one of the practical challenges associated with the use of those tools. But it's not inescapable, and you can go beyond sort of some of the there have been some recent developments that actually would inform things like the memory of these processes, because if you don't have a large scale separation, you start ending up with approximations that involve memory kernels, and those kernels are determined by the essential physics of the system. So you can actually start to build some of these things in.
I have a comment and a question in at the same time. This issue of trying to construct models which preserve certain physical laws. I mean, I can see why one might want to do this, but at the same time, isn't there a risk at some level? I'll give an example. So, for example, when talking, say, Navier-Stokes equation or some PDE, I might know that it conserves energy. Then I might try to construct a truncated model, something akin to a spectrally truncated numerical model, and I might want this projection, I might require that it also preserves energy, right? And then it's known in a number of examples that these truncated models have a different behavior. Even though they preserve energy, they will have a different behavior to the original infinite dimensional model.
Mm.
So certain solutions might be stable or unstable, vice versa, in the original PDE, while they will have a completely opposite behavior in the truncated version. So I'm just wondering whether this pressure on making approximate models preserve physical laws. I mean, where would the boundary be?
Well, I think one of the issues is when we're dealing with weather and climate models, we talk about them conserving energy, for example, but they don't. They're energy sources and sinks. And so what we're doing is we're properly accounting for these physical variables. And so if you properly account for the changes in the sink of the strength of a sink as you go to a coarser resolution, then you are still respecting the underlying physics, even though you aren't necessarily imposing a symmetry on your truncated system, which it would not really have.
what I want to do during the working group